Hello, everybody. This is Dr. Dave with Physics 152. We're getting a lot of questions from folks that are having a really hard time doing the algebra required from problem number 7, which is a circuit with several resistors in it, and you need to find the current flowing through it. So what I want to stress is there is one way to do it that involves this method called equivalent resistance. This is simply one method one can use. It is not the only method, and it's not always the best method. This is the most mathematical method, and for some people, it's the easiest method. So let me walk through this and tell you what it is. There's a concept called equivalent resistance, which we looked at last week in problem number 6. And that was if I were to replace, say, two resistors with one resistor, what value would it need to have? And this is kind of a strange concept. You might wonder, well, why would I have two resistors if I only need one? And that's fair. This is a mathematical trick that can be used for understanding circuits. And for our purposes, it's just a tool. It's just something we pull out of the toolbox when we need it. So if you have two resistors in series, what is their combined resistance? That's another way to think about this. And that is you can replace them with one resistor that's simply the addition of the two resistors together. And then what if you have two resistors in parallel? Now, what is parallel versus series? Well, in parallel, you could go through just one of them and exit and not through the other. So it's a little bit different. So the question is, if I were to replace this whole segment with something to get an equivalent resistance, what would it be? And as we saw in problem 6 last week, there is your result. And what's always interesting about this is the equivalent resistance for a parallel circuit is always going to be less than either of the two individual values. And the equivalent resistance for a series circuit will always be larger than either of those two values. So where did this equivalent resistance come from? As we saw last week, 1 over RAQ is 1 over R1 plus 1 over R2, which to combine these, we need to get a common denominator, which means I need to put an R2 here, an R2 here, and an R1, and an R1, right? This is what we're getting. We then combine that to R1 plus R2 in the denominator of R1, R2. But of course, this isn't what we want. We want 1 over this, which is how we get this result there. And so what you get here is R1, R2 over the sum of R1 plus R2. And you can plug in any positive values here and see that this fraction will always be less than either one of those two positive values. So how do we do this in practice? How do we actually solve this? Well, let's imagine we had a very simple circuit. This is just one battery combined with two resistors in series. So we always want to write down a Kirchhoff loop, even if we don't necessarily realize that that's what we're doing. So in this case, our Kirchhoff loop will start here. We'll go up to the battery, through this resistor, through that resistor, and back here. We know that the sum of potential differences around that loop is going to be 0. So there's going to be the voltage from the battery, the voltage difference from R1, and the voltage difference from R2. Again, we're treating all these wires as being ideal, meaning we're not thinking about any potential loss in them. We're going from low potential to high potential, so we gain potential of E, whatever that rating of the battery is. We flow with the current through the resistor. Remember, current's always flowing kind of down potential or downhill, sort of how you think about it. And as that current is flowing through R1, that's a drop in potential. How much? Ohm's law tells us IR. Then we drop here again, another IR drop. We know that the current here, so that the current through R1 equals current through R2, right? We talked about this multiple times in problem number 6. We can't lose any current in these circuits. And so we know I1 is I2. We can factor that out. And I'm just going to call it I now because I don't really need a label for it. That leaves with me R1 plus R2. In fact, this is precisely where the definition of series resistance comes from. But sometimes it's easier to just call it a Kirchhoff loop and solve it that way. So you can now solve for that current as just being the potential over the total resistance. Or you could approach this and say, I'm going to find the equivalent resistance of the circuit. Meaning what you're going to do is you're going to take these two resistors which are in series, you're going to replace them with an equivalent resistor in series. And so now you're going to say the potential difference is just IR. This is really just a Kirchhoff loop again. and the potential difference being IR gives you the potential difference is IR1 plus R2, or that's the current, which is, of course, the same value we got there. There's no difference here. So in a simple circuit like this, you could really do both things. I would argue the equivalent resistance is just probably a little bit more work than you need to do. It's not really that different. But when you get to a more complicated circuit, something that looks like the following, and this is way more complicated than we're asking you to do in problem number 7, but I wanted to illustrate what's going on here. And so what I want you to do is to look at this, and I want you to just pause the video for a minute and think about it. Ask yourself, how would I find the equivalent resistance of this circuit? What would I combine first? How would I go about doing it? There's a really important reason that we ask you to pause the video. Just like part F in this homework set where we ask you to make a prediction. Some people have said, can my prediction be wrong? Yes! Sorry if you're wearing headphones. Your prediction can be wrong. In fact, it's even better if it is. When we make a guess and we are found to be wrong, it means we learn more. It's a very clearly known result from social science. Social science will ask people to make predictions. Then they will be confronted with the results of those predictions, and when they find out they are wrong, they learn more. Can your predictions be wrong? You're damn right they can be wrong. And I'm sorry that anyone in science has ever led you to the idea that your predictions should be right. Your predictions can be wrong, and damn it, it's worth making them. Please pause the video and write down your best guess for how to do this. All right, thank you for pausing the video. What do we want to do? How do we want to think about this? What is our strategy? Well, the goal really is to get everything in series. So, what makes this hard? This parallel circuit. So I'm going to want to combine this parallel circuit first. But to do that, I need to combine these two resistors first, right? Remember that what I want to do for a parallel circuit is that kind of combination there. This does not look like that because there's this extra resistor. So the first thing I'm going to do is replace these two with a single resistor. All right. So I'm going to take R4 and R5. I'm going to combine them. I'm going to, instead of calling it like R6 or something like that, I'm just going to call it RA. And so 4 and 5 becomes RA. And what is the resistance of RA? It's R4 plus R5. Now here's where students make their lives harder. They won't write RA. They'll write R4 plus R5. Don't do that. You came up with a new letter. Use it. So now our new circuit looks like the old circuit, except we've replaced these two resistors with this new one, RA. What is RA? Well, if you ever need it, just go back to it. So now we can do a parallel circuit. And the parallel circuit, we go back to our model here, right? We recognize that for that parallel circuit, this is what we have. So it's just the two resistors multiplied together, divided by their sum. Easy enough. So what do we have here? The two resistors multiplied together, divided by their sum. Easy peasy. Call that RB. Now I draw my new circuit. So now I have R1, R2, RB, R6. What's that total resistance? Well, just add them all up because they're in series. Series is easy. So now what do? You would go back in and you would plug in whatever RB was, which is going to be this combination of things. You're going to have an RA. What is RA? Well, it's that thing right there. This is going to be messy, but it's doable. What would you do after you knew RC? Well, after you knew RC, you would say that, look, I have this circuit with RC. Okay. What do I know? Well, I'm going to know that the battery voltage, right, from my Kirchhoff loop, I'm going to go back to my Kirchhoff loop. The battery voltage from my Kirchhoff loop, right, is going to equal E, is going to equal this IRC. Okay. And now what is RC? I just plug in that value and I'm good to go. What do you want to do in the circuit in your problem? Well, you don't have to do this method. It's perfectly fine to do it with just straight up algebra. But if you want to do the method, this is what you're looking at. So once you combine this into an equivalent circuit, right, it's going to look something like this. And so what's going to happen here? Well, we know that the current leaves the battery, goes through this resistor, and splits. Right? So what are you going to find in this equivalent circuit? You're going to find the current that leaves the battery. Well, here, the current that leaves the battery goes through that. So what is that? You're going to find that the current in this circuit is I1. And that's going to help you do pretty much everything you need to do. There is a lot of algebra in this problem. But honestly, this is no harder than something you should have done in grade 10 or grade 11. Doesn't mean it's easy. But these are not new skills. This is not new mathematics. This is something you can do. You just haven't done it in a while. So yeah, it's a little harder. But I think you can do it. If you're still having trouble after this, please come see us in office hours. Feel free to message us on Teams. Thank you very much.